Hey everyone, my name is Henry Li Xingyuan. I'll be introducing JHU HLTCOE submission to the Voice Privacy Attacker Challenge 2025. As speech technologies permeate our lives, as companies rush to develop smart assistants like Siri or Alexa that take speech inputs, and as the popularity of voice chat platforms such as Discord continues to rise, so too has the importance of speaker anonymization. Let's define speaker anonymization within a concrete task. Automatic speaker verification. An automatic speaker verification system, or an ASV system, works as follows. It is assumed to have access to a number of utterances from one speaker, which we refer to as the enrollment speaker. At inference time, the system is given a single utterance per trial. The system is then tasked with deciding whether the trial utterance belongs to the enrollment speaker or not. How is ASV evaluated then? One of the most popular metrics is known as equal error rate, or EER. EER incorporates two different types of errors that could come up in ASV, false acceptance and false rejection. It makes the assumption that these two types of errors are equally damaging, and therefore their effects should be balanced out. In the case of many ASV systems, there is an adjustable threshold, which the system can be tuned with that threshold in order to be biased more towards producing false acceptances, or alternatively to producing false rejections. Therefore, generally, if someone would like to report the strength of the ASV system, they would change that tunable parameter such that the FAR and FR, the difference between those two values is minimized. Let's go into a bit more detail and put things in context of actual models and data sets. A very common way to do ASV is to train a closed set speaker ID model, such as an ICASSP model. And in order to ensure some degree of generalizability, the data sets that is being used to train these models typically have a large set of speakers. Examples of such data sets include VoxLab, which is perhaps the most commonly used benchmark for this task. Recall that ASV is an open set problem. So if at trial time, the speaker turns out not to be the enrollment speaker, it could in theory be any speaker in the world. In order to adapt the closed set speaker ID system for ASV and open set task, what people do is to detach the prediction head. Now we have a feature extractor which projects utterances into a space where utterances from different speakers are more likely to be separable. This was the idea behind X-vector systems, which were successfully adopted by many ASV systems. During the enrollment process, we extract the speaker embedding for the enrollment utterances. So that would correspond to the three blue stars in the diagram. We find a mean, which is represented by the dark blue dot. And then we set a cosine distance threshold. And then we consider every trial utterance whose embedding sits within that threshold from the mean, the dark blue dot, as an accepted utterance. By increasing the cosine distance threshold, which is the circle shown in diagram, from the dashed line to the solid line circle, we eventually end up with a threshold which gives us the minimal difference between the false rejection rate and the false acceptance rate. In terms of model architecture, most systems that are used in ASV tend to be relatively simple. They would often just consist of a few convolutional layers followed by an attention pooling mechanism, ICASSP being a primary example of that. In 2024, we participated in the Voice Privacy Challenge, where we were given the objective of removing personally identifiable information from speech. So in the context of the ASV task, we were tasked with changing or perturbing the original utterances such that the ASV system that I just described would no longer function. Successful submissions, including our own, achieved equal error rates of 40% or higher, essentially meaning that as far as the ASV system is concerned, the link between speakers and their utterances have been effectively severed. The attacker challenge, which is the one that we have just participated in, on the other hand, puts its participants in opposition to the submissions to the voice privacy challenge. In the attacker challenge, our goal now is to recover the links that had been severed by the voice privacy challenge submissions and match the speakers with their utterances. The baseline de-anonymization system in the attacker challenge was the same one that was being used for the evaluation in the voice privacy challenge. In this setup, a speaker verification or ASV system is trained on utterances that have been anonymized using the targeted anonymization system. As the ASV system has access to anonymized data, but not the anonymization system itself, the organizers of the voice privacy challenge dubbed it the semi-informed attacker. For the voice privacy attacker challenge, we find ourselves working under essentially the same constraints. We have access to anonymized training data, but we don't necessarily have we're not necessarily equipped to anonymize new data using submissions to the voice privacy challenge. Our submission to the attacker challenge targeted each of the 4 non-baseline anonymization systems. These include our own submission to the voice privacy challenge, codenamed TA-5, where each utterance is anonymized using either a voice conversion system known as kNN-VC or an ASR TTS cascaded system. The choice between these 2 systems is randomized for each utterance. And therefore, we dubbed it the admixture system. Other anonymization systems that we attacked are mostly based on either neural audio codecs or vector quantized bottlenecks, both of which employ a discretization process to remove excess speaking information from an utterance. Now we will proceed to discuss the improvements that we made to the baseline system, starting with changes to the training procedure of the backend ASV model. The baseline ASV model was an ICASSP model that was trained in 10 epochs with a fixed learning rate of 10 to the -4, and with no dropout applied to the model inputs. We found that both the number of training epochs and the learning rate appeared to be too low for many of the anonymization systems, which, due to their nature, present a harder learning task than the original ASV system was designed to deal with. And therefore, we increased both of these parameters, and we were able to get significant gains when either or both of these parameters were increased. We also experimented with adding input dropout with the hypothesis that doing so would improve the model generalizability of the ASV systems. Unfortunately, we were not able to find any performance benefits from using input dropout. Next, we will discuss using alternative distance metrics for ASV. Now, recall that in the baseline system, ASV is performed using Euclidean distance in the embedding space. So you can refer to the diagram on the right where a trial is accepted if its speaker embedding is sufficiently close to the centroid of enrollment utterance embeddings. So in this diagram, that would mean that all the blue circles, which are inside the big dashed line circle, or the threshold gets accepted, whereas all the green circles, which are outside the dashed line circle, which are too far away from the enrollment speaker centroid, they get rejected. Unfortunately, as many anonymization systems create badly behaving speaker embedding spaces and create many outliers, we found Euclidean distance to be a weak link in the baseline ASV system. We tried three different alternative distance metrics to address the outlier effect. The first one is to use the maximum similarity score or minimum Euclidean distance of the trial utterance to the set of all the enrollment utterances as the distance metric, as opposed to the distance between the trial utterance and the average speaker embedding as the distance metric. In this diagram, we can see that the top left blue star, the top left enrollment utterance, is clearly an outlier. And during trial time, it is completely ignored by the system. So each of the blue circles are close enough. These doubly arrowed lines are short enough such that the blue circles get accepted, whereas the two green circles get rejected. The next distance metric that we tried is what we dubbed the number of enrollment utterance speaker embeddings within the distance threshold. So this setup has the benefit of also having a tunable threshold, which is, as I mentioned before, very important for allowing us to compute a equal error rate. So let me explain the mechanism by appealing to the diagram on the right. So we see that the blue data point here, the blue dot, was accepted due to having 50% of the enrollment utterances within the threshold. So there are 4 enrollment utterances and represented by the blue stars, and 2 of them are within the blue dashed circle. So the blue data point gets accepted, whereas in the case of the green data point, it only has a single enrollment utterance, which is only 25% of the enrollment set, and therefore the green dot gets rejected. So this is another way that we came up with to reduce the outlier effect. And the last distance metric is a very well-known distance metric or technique used in ASV, which is known as probabilistic linear discriminant analysis. If you're interested, you can refer to the original paper, which is a very important work in this field. In our experiments, we found that PLDA was able to achieve consistent improvements compared to all the other distance metrics. Now, finally, let's discuss the last technique which we employ to improve the baseline ASV system, which is voice normalization using kNN-VC. So for some context, we observed that every anonymization system, including our own, mostly converts the speech from the source speaker, represented by my own picture in this diagram, to a target proxy speaker. And the randomization is done at a per utterance level, meaning that the speech from the same source speaker gets mapped into many different target proxy speakers. And this sort of mismatch creates a difficult learning problem for the ASV model, which now needs to ignore timbre characteristics and focus on other common speech characteristics. So in order to simplify this difficult learning problem for our ASV model, we experimented with voice normalization using kNN-VC. What we essentially do is we find a single proxy speaker represented by the cat picture in this diagram, and we map every anonymized utterance into the cat speaker. And by doing this, we obviously cannot recover the timbre of the actual source speaker. But what we can do is to remove timbre from the equation. So now, at least the model sees every speaker as having the same timbre, and therefore it has to focus more on the other aspects of speech, such as speaking style, accent, and all that kind of stuff, which can often leak through the anonymization system and can be used to recover the true speaker identity. Our best systems for each of the 4 anonymization systems are a combination of some or all of the techniques that we have described so far. Thank you very much, and please reach out to us if you have any more questions. Thank you.